If fusion is a star in a bottle, then here's the uncomfortable truth. Making the star is not the hardest part. The hardest part is where the heat exits, because in a tokamak, a sun-level heat stream gets forced into a tiny drain called the divertor. In the next few minutes, you'll understand what a divertor really does, why heat and particle exhaust is a make-or-break problem for power plant fusion, and why JT60SA's return in 2026 matters, because its upgrades help test the exact measurements and control strategies fusion needs next. No hype, no fusion is 2 years away, just the real engineering physics behind what's holding it back and what scientists are doing about it right now. A tokamak uses magnetic fields to keep plasma away from the walls. But energy doesn't vanish, particles don't vanish, so reactors create a controlled exit lane where heat and particles are guided down into special hardware, the divertor. Think of the divertor like a storm drain for a hurricane of super-hot plasma. Here's the issue. Experiments can pulse plasma and take breaks. A power plant must run at high power for long periods, repeatedly, reliably. So, the divertor faces extreme heat loads, constant particle impact, and material erosion that can contaminate the plasma. If the divertor can't survive and stay stable, fusion isn't a power source, it's a machine that keeps shutting down. And the weird part is, the solution is not just stronger metal. One of the most important strategies is called divertor detachment. Detachment means you intentionally make the plasma near the divertor cooler and denser, so a lot of energy is radiated or spread out before it slams into the surface. So instead of a cutting torch hitting tungsten, you're trying to turn that torch into a softer, wider heat cloud. Detachment is not a button. If you push too far, the plasma becomes unstable or performance drops. If you don't push far enough, the divertor overheats. So the real challenge is control, knowing exactly what the plasma edge is doing second by second. And that's where JT60SA becomes extremely interesting. If you like science explained without hype, subscribe. This channel focuses on accurate, visual explanations of the biggest problems in space and future tech. JT60SA is a major superconducting tokamak built through EU-Japan collaboration. It's designed to test advanced operational scenarios that help inform the bigger fusion roadmap. After early operations, it went into planned upgrades, and the plan is to return with commissioning and experiments in 2026. So, what's changing? In simple terms, upgrades strengthen 3 things fusion needs for the divertor problem: better measurements of the plasma edge, more control and capability through heating and hardware, and better understanding of how edge physics behaves at higher performance. Because if the divertor is your heat drain, diagnostics are your sensors, and control systems are your steering wheel. The exhaust problem is born at the plasma edge, the boundary between a stable, confined plasma and the region feeding the divertor. If you can measure temperature and density near the edge with high precision, you can keep detachment stable without losing performance. That's the kind of progress that makes future power plants more realistic. Because fusion doesn't fail in the core, it often fails at the edge. This is why European fusion programs have been putting so much focus on heat and particle exhaust. You can't scale fusion to a real grid power plant if the exhaust system can't run steadily for long periods. So when you see entire workshops and research programs centered on divertors and exhaust, that's not a side topic, that's the gate you must unlock. Fusion is often described as making a star on Earth. But the truth is, the future of fusion may be decided by something much less glamorous, a piece of hardware at the bottom of a tokamak that has to survive the heat of a star and do it every day. If you want part 2, I'll break down the divertor designs engineers are exploring, like different magnetic geometries and why some could spread heat far better than today. Subscribe so you don't miss it, and comment Divertor if you want that part 2 next.